This is Applied Calculus, Section 3.1, the constant e and continuous compound interest. We begin with the definition of the number e. Notice that e is expressed as a limit as n goes to infinity of 1 plus 1 over n to the nth power. And then they give an alternative definition of the value for e. Both of these limits will calculate this decimal of 2.718281, and it goes on. It is an irrational number. Because it is a never-ending, never-repeating decimal. We might ask, where did this expression come from? And one story I'm familiar with is in history, there was a family known as the Bernoulli family. They were involved in banking, and we know the compound interest formula tells us that a future value expressed as A is equal to the present value, or the principal investment expressed as P, times 1 plus the rate of interest divided by the number of times compounded per year, all raised to the number of compoundings times the number of years in the exponent. And the Bernoulli family posited how much money could $1 earn in 1 year. So they said let P equal $1, let R equal 100% interest, which is equal to 1 as a decimal, and let T equal 1 year. And if we put all of this together, we get A is equal to 1 times 1 plus 1 over n raised to the n times 1 power. And they said let the number of compoundings approach infinity. So let n tend towards infinity. And we can take our calculator and we'll type in 1 plus 1 divided by x raised to the x power. So I'm replacing the variable n with x, so it's compatible with my calculator. And then I can go to my table setup, make sure that the independent variable is set to ask, which it is. And in my table, I'll say after 1 year, that $1 becomes $2. After 10 years, that $1 becomes $2.50. And because we're going to infinity, we want the x value to grow very rapidly. So that's why I'm entering numbers that are much larger. And we see that when we get to 10,000 compoundings per year, that the value for E is, or the value for that $1 is 2.7181, 2.71828. So we're almost there. And we can say, well, let's go to 100,000 compoundings. And we see we get 2.7183. And we see, well, that 1828 would round to a 3. My calculator has limited space here, so it's rounding. So we see that we've got the values that squeeze the value for E, and that's what the value tends towards. So now we have this new value E, which is about 2.718281 ... and we refer to this as the natural base. Now, as mathematicians, we like to simplify things, and sometimes we don't want a fraction inside of the parenthesis, and we would like for it to be a simpler expression. So sometimes we just do a change of variables, and we say let S represent 1 over n. Then that allows us to rewrite the parentheses as 1 plus s, and we say that's much easier to work with. However, now our limit no longer includes the variable n, but now includes s. But we have to look at this for a moment and say, well, n was going to infinity. So 1 over 1 is 1. 1 over 10 is 0.1. 1 over 100 is 0.01. We see that as n goes to infinity and the numerator stays at 1, we're getting closer and closer to 0. So that means that s is approaching 0. Great, we've got that fixed. Now we just have to replace this n in the exponent and say, well, if s is equal to 1 over n, if we put s over 1 and cross multiply, we find that n is equal to 1 over s. And now our expression has replaced all of the n variables with s variables, and that's how we've gotten this new expression for e. And we do this because we never know how e is going to show up in our work. It can show up in this first way, in the second way. There are other ways that it can show up, and it is up to us to find out, well, how do we replace all of this algebra with a simple e to make our answers easier to calculate and express. So we like to be familiar with different forms of e so we can do that substitution. Here we'll take a moment to recap what simple and compound interest are. Simple interest is when only the principal earns interest. And we see that you have your principal and then you have interest on your principal. And you can factor out the p and get this other form of the simple interest formula. So a is equal to p times 1 plus rt. And we can give an example, let $100 earn 5% simple interest for 10 years. Well, then a would be equal to 100 times 1 plus, we need to express r, which is the interest rate of 5% as a decimal, so 0.05 times t is the number of years, 100 times 1 plus 0.05 times 10 years gives us $150. So here we have our A, which is the amount after the investment matures, but often our book will call this the future value. Here we have our P, which is the principal amount or the initial investment, and what our book will often call present value. Here they've switched the variable n to be m. They do the same thing, m equals number of compounds per year. And that shows up twice. And then t is the number of years. So if we take that same example from on top, but instead of $100 earns 5% simple interest, if we change it to compound interest, and let's say it's compounded monthly, that would make m equal to 12 times per year. We can now write a new formula, a equals 100 times 1 plus the interest rate is 5%, is 0.05 over 12 compounds per year, all raised to the 12 compounds per year times 10 years. And we see that the same $100 investment now matures to be $164.70. So it's the same 10 years, and we saw a $14.70 increase in what the money earned because the interest each year was earning interest. The interest each month was earning interest. So now we come to the compound interest formula for continuous compound interest. And the theorem states if a principal P is invested at an annual rate R, which must be expressed as a decimal, and it is compounded continuously, then the amount A, also called the future value, in the account at the end of 10 years can be calculated using this formula. A equals P times E to the RT power. And they give us an example here. It says if $100 is invested at 6% compounded continuously, as soon as you see that word continuously in there, that is what should set off that you're using the PERT formula. Compounded continuously means we want to use the natural base E. What amount will be in the account after 2 years? So we can say A is equal to 100 times E. We can say A is equal to 100 times E to the R, which is 0.06 times T, which is 2, all of that in the exponent, 100 times E to the 0.06 times 2 gives us $112.75. Then it goes on to say how much interest will be earned. Well, we started with 100, so we would just subtract that from the amount minus 100, and we get that $12.75 is the interest earned. So here we're going to graph the growth of an investment. The problem states Union Savings Bank offers a 5-year certificate of deposit, what is also known as a CD, and it earns 5.75% compounded continuously. Once you see that word continuous compounding, you know you're using E as the natural base. If $1,000 is invested in one of these CDs, graph the amount of time as a function over the period of 5 years. Graph the amount in the account as a function of time for a period over 5 years. So we're going to say amount as a function of time is equal to the initial investment of 1,000. Because it's compounded continuously, it's going to multiply a base of E raised to the interest rate, which is 0.0575 times t, because we want to write this as a function of time. Now we can fill out our chart here. When time is 0, 0 for t would give us an exponent of 0, and anything raised to the 0 power is 1. So we have our initial investment. No time has passed, so we still have our $1,000. Now let's calculate for all of the other years. So we're going to enter our 1,000 times E to the 0.0575 times X, because that's the variable we have available to us in the calculator, and hit enter. We're going to go over to table setup. It's set up to have the independent variable on ask, so I can enter the years I want. Well, I can change that to auto and start at 0 and increase the table by 1. So it'll give me 0, 1, 2, 3, 4, 5. And now I can hit second table, and I have 0 through 6 here. Okay, so we'll put these values from the table in here. 1059.20, 1121.87, 1188.27, 1258.60, and 1333.10. So now we're going to take these values and plot them. We're going to say that this is represented in a scale of thousands. So when we are at 0, our investment is at 1,000. When we were at 1, it is at 1,060. When we're at 2, it is at about 1,120. 3 is almost at 1,200. 4, 1,258. 5, 1,333. So we see that this is very much like a straight line, it looks like. And we might believe that it's a straight line because we're so zoomed in on the graph. The truth is that if we look at this graph from a distance, it will give us the true shape of it. Let me set up the window for graphing. We're going to go from 0 to, let's say, 10 years, counting by 1. So that's my x-axis. My y-axis will go from 1,000, because that's our initial investment, to 1,500, because we saw our account never exceeded that amount. And when I graph this, I say, okay, it looks a little more curved. Let me zoom out further. So I'm going to choose zoom out, option 3. And you can see more of that natural curve that comes with an exponential function. And the further you zoom out, the more of the curvature you should see. So when we're looking at just a small section of the graph looked linear, but as you zoom out, you understand the nature of exponential functions is it's got this extreme growth rate, but you don't see that always from the portion of the graph you're looking at. It's kind of like if you have a camera. If you zoom in too much, you don't see the whole picture because you zoomed in on one little speck there. You have to zoom out sometimes to see the whole picture. Okay, so here we have another example. It says, how long will it take an investment of $5,000 to grow to $8,000 if it is invested at 5% compounded continuously? And this is where we will use our relationship between logarithms and exponentials to solve the problem. We've done this earlier in the year. We're going to do it again here and now. So we'll write our function a of t equals, the investment is 5,000, so that's our p-value. The investment is 5,000, so that's our p-value, times e to the 0.05, that's 5%, times t, which is our time that we don't know yet. And it's asking how long will it take for it to be worth 8,000. So we would like to replace the a of t with 8,000. And now we want to solve for t. So the first thing we can do is divide both sides of the equation by 5,000. This will give us 8/5 is equal to e to the 0.05t. Now, anytime we like to get a variable out of an exponent, we need to do the opposite or the inverse operation, and that involves logarithms. So we need to take the log of the right-hand side that has the same base as e, and that's the natural log. So ln of e to the 0.05t is equal to ln of 8/5. From here, we can use our log properties, which say that we can use the power property to move this out in front. ln of 8/5 is equal to 0.05t times ln of e. And because ln has base e, this is going to be equal to 1. And we now have ln of 8/5 equals 0.05t. We want to isolate the t variable, so we will divide both sides by 0.05. And we will enter this expression in our calculator to get the approximate time it takes for this account to grow from 5,000 to 8,000. So we'll take ln of 8 divided by 5, and then we will divide that by 0.05, and we get 9.4 years. 0.4 times 12 months in a year is about 4.8 months, so approximately 9 years and 5 months. And that's two different ways we can answer it. Generally, 9.4 years should be what most of the homework will accept as an answer. But just to interpret, what does that 4.4 of a year represent? Well, 0.4 a year is 12 months. 0.4 times 12 gives us 5 months. So let's just run through a few application problems here. The first one says Provident Bank offers a 10-year CD that earns 2.15% compounded continuously. If 10,000 is invested in the CD, how much will it be worth in 10 years? So we just have to express the percent as a decimal, and we will enter this in our calculator, and we get 12,398.62. Part B says, how long will it take for the account to be worth 18,000? So now we're going to use that logarithm property. So 18,000 equal to the 10,000 invested times e to the 0.0215 times t. Our goal is to solve for t, which means we have to isolate it. So step one, get the coefficient of e out of the way, divide both sides by that coefficient. So the 3 zeros cancel, 18 over 10 becomes 9/5. Now we would like to get the variable out of the exponent, so we take the natural log of both sides. And the power property allows us to take the exponent and move it down and out in front of the logarithm. Now we see that we're left with ln of e, which is equal to 1, and 1 times anything is that thing. So 1 times 0.0215t is simply 0.0215t. Now to isolate t, we divide both sides by its coefficient. And this is the expression we need to evaluate in our calculator. So we'll say t is approximately natural log of 9 divided by 5. And then we divide that answer by 0.0215, and we get 27.34 years. Or 27 years, 4 months. Because 0.34 is about 1/3, and 1/3 of 12 months is about 4 months. The next application is asking about present value. A note will pay $20,000 when it matures in 10 years. How much should you be willing to pay for the note now if money is worth 5.2% compounded continuously? All right, so here our next application is using present value as the goal. A note will pay $20,000 at maturity 10 years from now. How much should you be willing to pay for the note now if money is worth 5.2% compounded continuously? So let's write our function a of t is equal to the principal times e to the 0.052 times t. This is what we're trying to solve for, and this value is the maturity value of 20,000. So $20,000 is equal to P times E to the 0.052, and we have 10 years times 10. And when we're all done, we should always have just one unknown variable. So here I had 2. I still had more information I can plug in. I had the number of years t. Now that I have just one unknown variable, I can solve this. And this whole expression here, I'm just going to enter into my calculator so I can replace it with a number. E raised to the 0.052 times 10 gives me 1.682. So 20,000 equals P times 1.682. And we'll divide both sides by that. And that tells me I should be investing about $11,891. So this type of math can be used for planning retirement. If you have a certain amount of money you would like to have available at your retirement time, or if you're trying to save for a house and you want to have a certain amount of money for a down payment, you can anticipate how much money you should be putting aside so that you reach a certain maturity rate in 10 years' time or 20 years' time, if that's how far off it is till retirement. So here's an application with radioactive decay. A mathematical model for the decay of a radioactive substance is given by Q equals Q sub 0 e to the RT. Well, Q sub 0 equals initial amount. And we've seen sub-zero notation before. We'll continuously see sub-zero notation. That is always at time 0. Often with tracking the spread of infectious diseases, they'll have a patient 0, and then the spread rate. We can have an investment 0, a radioactive decay at 0. It's all talking about at time 0. And when we're talking about at time equals 0, that means the initial occurrence, or the initial amount invested, or the initial quantity that was obtained. And we can talk about population models. P0 is the initial population before it grows or diminishes. So anytime you see a subscript of 0, we understand that to be an initial amount. So now they describe all of the variables. Q sub 0 equals the amount of the substance at time equals 0. R equals the continuous compound rate of decay. T is time in years, and Q is the amount of substance at time t. So another way you can write this is Q of t equals Q sub 0 e to the RT. If the continuous compound rate of decay of radium per year is given by this R value, and because it is already a decimal, we don't have to do any conversions, how long will it take a certain amount of radium to decay to half the original amount? This is known as the half-life. So we can So when we're talking about half-life, that means we want the quantity to be half of whatever we started with. So we put the number 1/2 in there, equals, and we put 1 in for the initial amount. E to the RT, our R value is negative 0. And then we have 0.004332 and T. And they're asking how long is it going to take for it to reach this half quantity. And the only unknown variable here is T. So we simply have to solve for that. Again, because it's in the exponent, we need to use logarithms. Because the base is e, the logarithm we're going to use is ln. So ln of 1/2 equals ln of e to the negative 0.00043332t. And we understand that this number is going to come out front. and that the ln of E becomes 1 and cancels. So now we can divide by the coefficient of the t value, and we'll enter natural log of 1 divided by 2, hit enter, and then divide that by negative 0.0004332, and we get 1600 years. The half-life of radium is 1600 years. And generally with radioactive elements, that is how we communicate their quantities and how they decay in terms of half-life. So plutonium will have a half-life, radium will have a half-life, and this is the reason why we like to avoid radioactive or toxic radioactive waste, because it takes so long for it to decay and it becomes a hazard to the environment. Okay, so that's the end of this lecture. Go back and watch it again, follow along with your notes, try the practice problems, and come to class with questions.